Hello and welcome to Top 4.1. Translations and reflections is a kind of a weird thing in geometry. And believe it or not, there's no proofs in this section or in this topic, actually. And it's just like a nice little retreat from what we've been doing. So here we go. It's a breath of fresh air for some of you. A transformation is a function. So a function is something that you put something in and it spits something out. Okay, so it's a function that moves or changes a figure in some way to produce a new figure called an image. The image. The image is what is spit out of the function. Another name for the original figure is the pre-image. That's the original figure. It's like when you look in a mirror, you see the image. You are the pre-image, and you see the image. It's after the reflection, you see your image. The points on the pre-image are the inputs for the transformation, and the points on the image are the outputs. You put your pre-image into the mirror, it outputs your image. A rigid motion is a transformation that preserves length and angle measure. Another name for a rigid motion is an isometry. That's a new word, isometry. And so here are our four transformations: translation, reflection, flipping. Translation is like a shift. Think of it like a shift. We're just shifting left or right, up or down. Reflection is like a kind of like a flip. We're flipping it over the line of reflection. A rotation is like a turn. We're turning it, turning. And a dilation is like a scale drawing kind of. It's like a compression or an enlargement. Compression or enlargement. So in these four types of transformations, three of them are rigid. Three of them are isometries. These mean the same thing. So this one, the shape did not change size. And if we flip it, the shape, it does not change size. If we turn the shape or rotate the shape, it does not change size. If we dilate the shape, it does change size. So these three are isometries. And another way of saying that is that these three are rigid transformations. All right, now today's lesson is on translations and reflections. All right, so here we go. A translation is rigid, preserves the shape, size, that moves every point of a figure the same distance in the same direction. More specifically, a translation maps. That's the technical word for moving. It maps. So like here, this figure was mapped to this figure. This point was mapped to this point. So if I use the word mapping, that's what I mean by that. So it maps or moves the points A, B, C of a plane figure along a vector. A vector, which we write a vector like this, and we'll talk about a vector in a moment. It moves along a vector. A moves to the point A prime, B moves to the new point B prime, and C moves to its new position C prime. So like here, we're going to take this figure and translate it here. This point moves to this point. So A moves to A prime, B moves to B prime, and C moves to C prime. And with this notation like it is, you can see that this is the pre-image, and this is the image because of the primes. This is the vector. The vector is how you move it. The vector tells you your left and right movement and your up and down movement. So with a right movement and an up movement, we get this vector right here. So a vector, is a quantity that has both distance. Let's not call it distance. Let's call it magnitude and direction. And if you're a fan of Despicable Me, that's a quote. A vector is a quantity that has both magnitude and direction. So the magnitude of a vector is the length of it. And then the direction is kind of like the slope. It goes over and up. It goes over 6 and up 2. It goes over 3 and up 1, over 3 and up 1. It's like slope. And is represented in the coordinate plane by an arrow. So there's a vector. This is our vector. And this vector is the same as this vector, and it's the same as this vector. As far as these vectors are concerned, they're exactly the same because they have the same length and they have the same direction. Even though they're in different positions, they're the same vector. In the diagram, the initial point or the starting point of the vector is C. So let's go back to our original vector. The original point was C. And the terminal point, which is where it terminates, was C prime. So it started at C and ended at C prime. The vector is therefore named vector C, C prime, like that, much like a ray. And so this is the way we write vector. It's kind of like a ray. A ray is like this, and a vector is just like that. The horizontal component of the vector, that's how far you go to the right, is 1, 2, 3, 4, 5, 6. And the vertical component is 2. And so therefore we can write the vector in component form, and it uses the horizontal and vertical. So the component form of the vector is like this: 6, 2. That's the left and right and the up and down. It goes 6 to the right and up 2. This vector would go 6 to the left and down 2. So it would be the opposite direction. Those would be opposite vectors. All right, with that said, let's do some examples. Example 1. It says segment XY is given by the two coordinates, -2, 3, there's X, and 1, 2. And there's Y. And we are going to translate using the vector 1, -4, which is 1 to the right. Let me draw that segment, by the way. This was segment XY. We're going to move every point 1 to the right and down 4. That's what that means. So we're going to take X, we're going to move it 1 to the right and down 4. So this is now X prime. And we're going to take Y, move it 1 to the right and down 4. And there it is. There's the new, this is the image. It's after the translation. Okay, use the vector to translate. We check. State the points. So the point -2, 3 gets mapped to this point, -1, -1. You can see that we don't need a graph to do our translation. If you take -2 and combine it with 1, you get -1. And if you take 3 and combine it with -4, you get -1. So you don't need a graph. So for example, the point 1, 2, what's 1 combined with 1? 2. What's 2 combined with -4? -2. Is that the point 2, -2? Yes, it is. So you don't need a graph to do this. Graphs help, but you don't need a graph. All right. Example 2. The image of triangle ABC, that is triangle ABC has A prime, which is at 0, 3, B prime, which is at 2, 4, and C prime, which is at 1, 0. So there's that triangle right there. What are the coordinates of the pre-image if the translation vector was the following? So this is the result. This is our vector, and the vector goes -3. So if we started here, for example, it would go -3 and down 2. So that's the vector we're working with. So we got to kind of do the opposite. We're going to go over 3 up 2 right there. There's C right there. And you can see that we're using this vector to get from here to here. We go over 3 and down 2. This is where C started, and this was the image. Now do the same thing with A, go backwards. So there's A right there, and B has to be right there. Okay, so this is in this scenario, we went from the pre-image to the image. And in this scenario, we're going backwards. So to do this by hand, so for the point 0, 3, if this is the pre-image, sorry, if this is the image, the pre-image had to have been, you subtract. So you got to go backwards. So you got to add 3. And then instead of subtracting 2, you add 2. And you can see that this is the point 3, 5 right here. But there it is. So you have to be careful in what they're asking. Are they asking you to go from the pre-image to the image? Or are they asking you to go backwards? Are they giving you the image and asking you to go to the pre-image? All right, example 3, this one does not have a graph. Let's see how we can work this one out. The pre-image has vertices R, S, and T, and the image has the points R, S, R prime, S prime, T prime. What is the rule of the translation? So how did I get from, say, R to R prime? What did I combine with 2 to get to 7? So the vector would look like this. 2 plus 5 is 7. 2 minus 9 is -7. So that's the vector we're looking for. This is the vector that takes you from R to R prime. Let's try. What's 5 plus 5? 10. What's 2 minus 9? -7. So this is our vector. And now there's something called a rule of a translation. So the rule of a translation looks like it's just another way of writing a vector. And it takes any point xy and maps it to x plus 5 and y minus 9. It's the same idea. It means you're going to take your 2, you're going to add 5 to get to 7. You're going to take your 2 and you're going to subtract 9 to get to -7. This is called the rule. That's how you write what's called a rule of a transformation. All right, next. If P prime is 4, 5 and the vector is -5, 7, what is P? So in this scenario, you've got P prime, so you need to go backwards. P is this point, which maps to P prime, which is 4, 5. So we got to go backwards. So what do I start at? Combine it with -5 to get to 4. What is 9 combined with -5? 9 combined with -5 is 4. What do I start at if I combine it with 7 to get to 5? Blah plus 7 is 5. -2. -2 combined with 7 is 5. So this one I was kind of going backwards. I had to find the beginning point from the end point. That is probably the hardest thing that my students have with this lesson is that they get confused with